Okay, I have an announcement concerning the program. So Lorzana will be giving, in fact, her seminar, but by Zoom at the end at 4:20. So we'll have in order first Remi Lam, then Marc Bocquet, and then finally Lorzana at 4:20 on climatology. And I give the microphone to Pierre-Louis Lyons, who will be the animator of the second part.
That's just because he doesn't want me to ask too many questions. So if I'm a chairman, I will have to restrain myself. Yes, we are very happy to continue to resume this series of beautiful lectures. And this afternoon, Remi Lam, DeepMind, Google DeepMind, and MIT. And I'm not going to repeat the title, which is just there. Thank you very much.
All right, can everybody hear me? Yes, okay. So thank you very much for the introduction. I'm really honored to be here today to present to you some of the work I've done with my colleagues at Google DeepMind over the past few years. I'm not at MIT anymore, so that thing slipped into the bio, but I'm now at Google DeepMind, where I am a staff research scientist. So maybe something I want to say is that there's a lot of hype around AI, and sometimes it's really easy to go over the flashy details. And so today I'm really glad that we have 60 minutes to talk about some of the work that we've done, so we can go a little bit more into the details of how things work, what doesn't work, what you have to be careful about, and hopefully I'll talk about some of the things that we've learned on the way that can be useful to you. I also want to thank the organizer for this very nice program. You've heard about many different approaches on the spectrum, from fully physics-based approaches with the quasi-Hamiltonian methods. You've heard about hybrid approaches with neural GCM combining equations and neural network. You've heard also about pure ML methods from Claire, and I'll be purely on the data side, basically. No equations so far in my work. And I think you can see that in the slides where I think the quasi-Hamiltonian equation slides had many equations. Michael had few equations in the presentation, Claire almost none, and I will have 0 equations. So hopefully you're not too upset about that. Maybe a little bit of context before we start this discussion. So I joined DeepMind in 2018. I did my PhD at MIT. I was in the aerospace department. So we were doing very much, PD solver equations, things like that. I wrote PD solver myself, and I came at DeepMind wanting to do machine learning, but I came with that prior that, physics was very important. Those equations are very elegant. I love them. And at the time I joined, there was DeepMind was kind of transitioning from working in kind of game environment, so you can think of Go, some other kind of virtual environment, and they were really in the midst of transitioning from those kind of artificial simulation environment and going towards real world data. And I came there and I learned about this kind of principle that Richard Sutton, his famous professor working on reinforcement learning, talked about a lot, which is the beta lesson. And the beta lesson is essentially, time and time again in machine learning, we relearn that you can try to add inductive biases, but if you have a lot of data, it's just much better to find a very generic and powerful architecture and let the data kind of drive the process and kind of take a step back, not add too many inductive biases, just the bare minimum, and kind of, if you have a lot of data, just let that drive the process. And so with that state of mind, basically, I came there and there was this project on weather forecasting, nowcasting, so precipitation prediction at very short lead time. And that was the very natural first step for machine learning to try to do weather forecast, because the data is radar data, it's very messy. Traditional approaches, PD solvers are really bad in that regime. And so it felt like a natural step to kind of try to do something. We used GAN at the time, and they worked pretty well. And then the next step was to think about longer time scale, and we thought about medium range. And it was not very obvious at the time what this would work. We have those equations, they work pretty well. It's a very mature field. People have been working in this field for decades, so why would that work? And so, at DeepMind, we had a lot of freedom to explore new ideas and kind of come up with projects and just try things. And that's kind of gave rise to the GraphCast and kind of GenCast papers. So I'll be talking a little bit about that today, and hopefully I'll have plenty of time for questions. So if you have anything you want to ask, feel free to interrupt me or write down the question for the end. So I want to start by giving kind of maybe a lot of you know about the traditional way of making weather forecasts, which is to use numerical weather prediction systems. And those are extremely well-designed machines. They simulate the entire weather system, converting many equations into algorithms that are kind of solvable numerically. There've been some really great advances with those models. In part, doing better science, better modeling, better algorithm, better data assimilation, and also better hardware. We know that if we put more computational power and discretize those equations on a finer and finer grid, we should get better results. And to some extent, that combined with data assimilation, that's been one of the main driver of progress in that field. So putting more compute behind those equations that everybody knows and trusts. But there's some challenges, and one of them is that improving those models requires significant expertise and computational resources. We've heard, for instance, the talk about quasi-Hamiltonian, that was pretty complicated to follow for me, at least. And so it requires really knowing a lot of things to kind of make progress there. And another limitation is that despite having access to a large amount of weather data, it's quite an open research how to use and leverage that data in those traditional models to improve the forward path of the model. So we came to start this project, and we took this approach of using machine learning to make a forecast, and there's many different advantages that we thought about. Machine learning is extremely flexible, readily applicable in a wide range of physical problems. You can pretty much take the literature in Europe and kind of try to apply it to a new problem, and that would work typically. You'll get some results out of that. Yes, so there's also it's extremely efficient. It can basically work on coarser data, both in time and space. I think that's something that is a little bit underappreciated right now, that the quality of the forecast doesn't depend on the resolution of the data you work with. In traditional, with PD solver, you really are familiar with the fact that if your grid is too coarse, you're going to miss the dynamics. Your equations are going to not be resolved in an appropriate manner. In ML, actually, we learned directly from the data, and we managed to get model extremely performant, even though the data was at, for instance, 1 degree resolution. So that would be way too coarse for a traditional model to really perform very well. So there's this decoupling a little bit about the resolution and the quality of the dynamics that you can generate with a model, which I think is something that people don't really appreciate fully. The second thing is that it's really fast to develop. We started the project on GraphCast maybe 2021, and we had GraphCast by the end of 2022, so the development loop was pretty fast. And then when the model is trained, which can take some time, then the forecast is extremely fast. So that can enable all sort of decision making and reduce the latency of our forecast, which can be really useful in certain applications. I think the main message here is that machine learning can both leverage the computational power that we get with those new accelerators that are available, but also the data. And really, this is two leverage that we have. We can put a compute axis, but also we can really leverage all the data that has been collected over years and will be collected in the future. So it's really providing us kind of something different to make the prediction better. So maybe we started that project thinking about transforming global weather forecasting with machine learning. And I want to just take a second to talk about the word transforming. There's many things you can use a PD solver or an NWP for, and our goal was to really make the best weather forecasts with ML method. There's many things you can use with an NWP for. You can try to understand what variables are important, sensitivity analysis, all sort of things. What we've done was specifically to improve forecasts. So there's certain things that this model is not optimized for, and for which traditional models are still very, very useful. So just to set the stage, our model is trying to predict the weather everywhere on Earth, both at the surface and the atmosphere. So what we call atmospheric variables, so 3D variables. GraphCast was about making 10-day forecasts at high spatial resolution. And high spatial resolution means that the grid on which the data we make the prediction for is at 0.25 degree resolution. That's roughly 30 kilometers at the equator. And basically, we predict many, many variables. I'm just showing 3 out of the 227 that GraphCast predicts. You can see the surface wind on the left, surface temperature in the center, and temperature at 500 hectopascal in the right. And really, the takeaway message is that machine learning really brings a paradigm shift in the way we do weather forecasting. We're learning directly from data. You've heard many times about this reanalysis data set, ERA5, from the European Center for Medium-Range Weather Forecast. We also, for our operational model, we also use HRAS data, which is the data from their operational forecast model, the deterministic one. But everything is learned from data. There's not a single physical equation that we solve in that problem. It significantly outperformed the industry operational gold standard on a large number of metrics. And the predictions are actually useful. They can actually support certain type of planning for, I shouldn't say extreme events, but maybe severe events. And I'll go into the details of some of this application. And again, it's much faster to make a forecast, and therefore it also makes the research in weather forecasts much more accessible. You don't need a supercomputer nowadays to try a new idea. You can start from some of the code we've open source or some of the train weight that we've made available on GitHub. And in general, you can do a lot of progress and do a lot of demonstration that something works with a few GPUs. All right, so why now? I think there's 3 key features that Michael talked a little bit about, but I really want to emphasize. One is about data and benchmarks. So we're really kind of standing on the shoulder of giants here, where we've taken some of the publicly available data called ERA5. It's a massive data set, 40 years of data, very high quality. A lot of work has gone into making that data very high quality and available, and also a public benchmark. So there was this paper, I think around 2020, 2021, called Weather Bench. And that paper was essentially saying, okay, take that data and try to optimize for this metric. Try to predict geopotential at 500 hectopascal, temperature at 2 meters, a few other variables, but just try to do that at those lead time, maybe 6 hours ahead, 2 days ahead, 3 days ahead. And what that did is essentially putting 2 communities together, people knowing about weather forecast and people knowing about machine learning, and telling them this is how you should interact and how you measure success, how you measure your progress. And I cannot emphasize enough how much that public benchmark has been instrumental in the progress we've seen in the past few years. The second aspect is compute. GraphCast, for instance, is trained on 32 TPUs, which is much smaller than the picture I'm showing that, so that's 1 TPU. At inference time, it takes about 47 seconds, I think, on a single TPU to make a 10-day forecast, and that's in comparison to about an hour on tens of thousands of CPU for a traditional PD solver. And there's no need, there's no need for a supercomputer, so that makes it much more accessible. And on the right, I've said, there's a lot of deep learning algorithm, a lot of methods that have been open source. The papers and the methods are, described in paper widely available. I don't think the specific details of the models are important. You see paper with transformer, convolution network, graph neural network. I don't think that's really the key here. We're at the point where we have architecture that are extremely expressive and powerful, and we can do a lot with them. I just wanted to cite a few papers that kind of came out around the time where we also made our work available, and cite, this is non-exhaustive obviously, CNN method, GNN, FNO also from the NVIDIA teams, transformer that everybody hears about, hybrid methods such as neural DCM. But the point being that there's been an explosion in research in weather forecast with machine learning in the past few years. I just want to, this slide is really to mention something that I don't think is, again, valued enough, which is the sheer scale of the data in weather. This is just, an MNIST sample, which used to be the standard for doing machine learning research a few years ago, ImageNet, and this is a single frame of ERA5 at quarter-degree resolution. And that's for a single variable. And as I mentioned, GraphCast model, 227 variable, and when we're on the road for 10 days with 6-hour steps, that's 40 steps. So that's really a lot of data. And in order to make those models work, a big part of the work is in engineering. And I don't think we should shy away from that part of the work, which makes a lot of things work. In LLM world, also, we've seen a lot of progress with sheer scaling, but also extremely good engineering. And I just wanted to kind of highlight that this is a very important step of the research here. Another question I want to answer is machine learning only emulating NWPs? How come you can do better than NWPs if the data comes from this reanalysis that is generated by those NWPs? So if you pictorially, and that's a very gross simplification, if the true weather state is this trajectory over time, and you imagine that this dashed red line is a forecast made by an NWP, eventually it diverges from the true trajectory. And so there's this process called data assimilation where you collect some observation from radar satellites, and you do that data assimilation and you correct your state. You get closer to the true trajectory. And then you unroll your model further in time, you correct it with observation, etc. And so the reason that we're able to do better is because those models that we learn, they don't learn from the red dash line, they learn from the point after correction, where you're closer to the true trajectory, supposedly. And so we're not just emulating those red arrows, we're actually trying to kind of do something where we're learning state that have been corrected and grounded by observations. So now I want to tell you a little bit about GraphCast, which is the deterministic model that we published a few years ago. That was published in Science, and I want to just highlight a few of the collaborators I work with. This is a relatively large team, I would say, and that was published in 2023 or 2022. And the idea of GraphCast is to learn to make a prediction, and we're using graph neural network in that specific instance. So the way the model works is that you have some description of the weather state, which is global. It's like data from era 5, covering the entire world. And then with GraphCast, you make a prediction for what happens at the next time step. So in our case, that's 6 hours away. The way we make this prediction is, as the 3 following components, there's an encoder. So this encoder works as follows. You have data on the grid, multiple variable, multiple pressure level, and you encode that with a graph neural network in what we call a latent variable that is on a multi-mesh, and I'll describe what that is. But basically, this is transforming something you can really physically understand, temperature, specific humidity, and transforming it into a latent variable that the model can learn from and work with. The second part of that model is a processor, and that processor works on this very complicated mesh that I'll describe in a few seconds, and it operates by an algorithm called message passing that transforms kind of the latent variable sequentially and propagates information over space, and we do that 16 times before going to the next phase. But first I want to describe a little bit the mesh. We call that a multi-mesh. I don't know if there's another pre-existing name for that. We start with an icosahedron, which is this figure here on the bottom left. And that icosahedron we can kind of increase the resolution of that icosahedron by dividing every triangle into 4 smaller triangles. So you can see this triangle here, become this triangle here with 4 little triangles, and we can repeat that process iteratively multiple times up to that level of the mesh here. So the multi-mesh here is all the nodes that you have in this sphere here, and the collection of all the edges you got from all the intermediate stages. So that means that big mesh here has something like 41,000 nodes, and more than 300,000 edges. Some of them are very small edges, and they're very useful to kind of process and propagate information and process small-scale type of phenomenon. And at the same time, you have much longer edges, here very, very long, that are very efficient at propagating information and transporting information in space. And so that part of that structure that we're using is actually quite important when you're processing the data to make sure that it propagates far enough. So after this processor step, you have a decoder. So now you have the latent representation on that multi-mesh that you've computed via message passing step, and then you just decode into the latitude-longitude grid in variables that you can actually understand, so specific humidity, temperature, etc. And you've done all of that without any equation solved. It's all graph neural network that are parameterized by parameter that you learn directly by gradient-based approach. And once you've done a prediction at the next step, you can just unroll the model autoregressively, like a typical weather model. All right, so that's kind of GraphCast in a nutshell. I just want to give you a little bit more detail about how it's trained. As I mentioned, it's trained on 40 years of reanalysis data, so era 5, and the learning is driven by an autoregressive loss. And the reason for that is to penalize long-term error. So what this means is that once we train the model, we take a sequence of data from our training set, we put the input into the model, it makes a prediction for what happens in 6 hours, we take that prediction, we feed it back into the same model, we make the prediction for what happens in 12 hours, etc., and we unroll multiple steps, and then we compare that sequence of prediction to the ground truth that we have in our sequence. and then we backpropagate the loss in time. So essentially, we're penalizing the model for not only making error at the first step, but how this error is going to compound over time up to a certain horizon, in that case, 3.5 days. And so there's many reasons to do that. One is to make sure that the error doesn't compound too much. You also want to make sure that the model understands the type of error it introduced in the prediction and the consequence this will have at the next unroll. So that's quite important, or at least we believed at the time. It's also like it makes it much easier to kind of regularize the model. You're trying to learn, you have more signal for the data you have, essentially training like that. So that's one thing I wanted to touch about. If you look at the, this part is actually extremely expensive. The autoregressive part is very expensive because it's a sequential operation. You have to keep a lot of things in memory in order to backpropagate. So this part is very expensive, and we try to kind of minimize how much time we spend doing that autoregressive training in our training phase. So at the bottom left, you can see like 3 plots. They describe 3 different phases. So in orange, you can see the learning rate, where there's like kind of a ramp-up period for the learning rate, then there's a cosine decay, and then it's a flat, very small learning rate at the end. But the important part here is that during phase 1 and 2, if you look at the purple curve, it says one autoregressive steps. That means that for roughly 300,000 steps of training, we only train the model to predict very well the next step. That's the only thing we do. And that's because this is much cheaper to do. And then at the very end, from 300,000 steps to 310,000 steps, we ramp up the number of autoregressive steps. So every 1,000 steps, we just say, well, now have 2 terms in your loss, 3 terms in your loss, 4 terms, up to 12, which corresponds to like 3 days of supervision. And so the cost of this phase really ramps up really quickly, so that's why we would try to minimize it. One thing I want to touch on is that there's a lot of decisions that go into defining the loss, and that can influence a lot of things you see in results. So the loss is a single scalar number. Obviously, that means that when you're making a prediction of many, many variables everywhere in the world, you have to decide on a way to aggregate all of that information into a single value, right? So you have to decide, if I want to predict temperature and specific humidity, how much do I care about one versus the other? So that's an important decision that you have to make. In our case, we try to normalize the data so that like the prediction are in the 0-1 range, and then we just sum them. But you also have to decide how much do I care about predicting very well the variable close to the surface, which affects us the most, versus what happens very high in the atmosphere, which might be very important for the dynamics of the model, but doesn't affect users in the same way. So in that work, we made a design decision, which is to weight the pressure level at which we made the prediction based proportionally to the pressure. So if you are at very low pressure, so very high in the atmosphere, the weight associated with that term in the loss is going to be very low, while if you are at very high pressure, so close to the surface, the weight is going to be very high. So we're training the model to be very good to predict the surface variable compared to very high in the atmosphere. And I'll show some results that kind of reflect that decision. But that's just a decision, and you can pretty much do whatever you want to fit your use case. Another thing I want to touch on is like how we thought about like dividing the data to train the model, and we really took a lot of effort to make causal splits and really test for deployment generalization. So what I mean by causal is that in our case, we wanted to test on data from 2018, and we wanted to make sure we're not fooling ourselves by thinking the model works very well. So to avoid data leakage and meta optimization, because we're at Google where we can afford to make a lot of design decision and train models, so it would be very easy for us to meta optimize. We have completely separated the development phase from the test phase, and in the following way. So during the development phase, we change the architecture, we search through hyperparameter, etc. We define the training protocol and the stopping criteria, and we do all of that training on like 1979 to 2015. And then once we've trained the model, we use 2016 and 2017 as validation. And we iterate many months on that. We make hypotheses, try new things. And once we're happy with that, we freeze everything here. All the decisions here are frozen. The architecture, the hyperparameter are frozen. The training protocol, stopping criterion, everything is kind of, okay, that's it. That's what we do. We freeze the protocol, and then we retrain the model on all of the data available, including 2016 and 2017, and we report the result in 2018. At this point, we've committed to putting the result out there. And that separation was very important to make sure that the model never gets to see data from the future, because obviously you don't have access to that. And we're confident that the results are going to generalize properly over time. I just want to talk a little bit about the evaluation protocol. So I had some questions before the presentation about how we go about comparing model. So we compare GraphCast to the deterministic gold standard by the European Center, which is called HRES. So that's the deterministic version of IFS. But those models kind of use different initial conditions. So what we did to be as fair as possible to the model is to compare GraphCast to its own initial analysis, essentially ERA5, but HRES, which is not initialized with ERA5, we compare it to some data that makes sure that it has 0 error at lead time 0. That's a data set that we call HRES FC0, and in the next slide I'll explain a little bit what that is. So if it's midnight and you get some observation, you do data simulation, you get this red square, HRES is initialized with that, and then you make a forecast for the next 18 hours or more. 6 hours later you get some new observation, new analysis for HRES, it can be unrolled in time, that's more prediction, etc. So HRES FC0 is the collection of those red square, and when we compared HRES performance, we always compare it with that data set. So that means that at lead time 0, comparing to itself, 0 error, and then at 6 hours, it would have some error with respect to that point. But that ensures that HRES is not penalized by being compared to something it's not really meant to be compared to. Just to illustrate that point, I want to show how, if you evaluate the performance of HRES, so our baseline, against ERA5, which is in red, and you compare the same forecast but to ERA5, which is in red, so the opposite, to ERA5 in red and to that data set I mentioned, HRES FC0 in black, this is the performance you'll see. So there's a bit of difference at shorter lead time, and then it tends to be the same at longer lead time for most variable. And the one that really makes a difference is temperature 2M. So you can really fool yourself into thinking you're outperforming the HRES baseline if you compare to the wrong thing, essentially. All right. So now I'll show some aggregated scores. So this is like the geopotential at 500 hectopascal, which is one of the variables that Michael was showing earlier. Root mean square error as a function of lead time. In black, you have the baseline HRES, and in blue, you have GraphCast with error bars. If you can look at the relative preference with respect to the other, lower being better here, so you can see that GraphCast is 15% better here, and maybe 7% better at this lead time. And you can do that for many variables. So, we do that, we verify against a lot of variables because we don't want to cherry pick the result. We want to make sure there's no blind spot, essentially. So you can see temperature at 2 meters, 10-meter wind, and the humidity at 700 hectopascal. And you can see for different variables, we do more or less good. And maybe, yes, that's just 4 variables. We can push that even further and use the protocol that ECMWF used, which is to use a scorecard. And in a scorecard, you have, for instance, for one variable and multiple lead time, you look at many different pressure levels. So that green line here corresponds to the plot I showed in the previous slide, and you can repeat that for multiple pressure level. And you can do that for multiple variables. So when we look at that full scorecard, that's roughly 1,400 targets, GraphCast outperform HRES on 90% of them. And actually, you see that where it's not outperforming is at 50 hectopascal, which is pretty high in the atmosphere. And if you remember correctly, that's where we put very, very little weight in the loss function. Something I wanted to touch upon, because we talked about generalization for climate model. One experiment we did is to look at, after training a model, how long is this model good for usage, basically? And so this plot shows the relative performance that has been normalized by a version of GraphCast trained with data up to 2018, but not including 2018, and comparing it with other GraphCast models that have been trained with using one more year of data, so up to 2019, up to 2020, up to 2021. And all of the models are compared on 2021. So essentially, it's different versions of the same model that have been using fresher and fresher data. And what you see is that the blue line is the GraphCast using the oldest data, and the other model using fresher data gets slightly, a little bit, but consistently better over time. And what that suggests is that we're not going to be adapting to climate change or being able to really predict climate change with that, but that suggests there's maybe a mechanism that kind of automatically adapt the model as we get more data and maybe distribution changes a little bit. So I just wanted to include that slide because some comments were made about what happens in terms of generalization and distribution shift.
I'm sorry, was it affected by the lookout?
Sorry?
Was it affected by the lookout?
The lookout, what do you mean?
The lookout during the COVID?
I don't know about that. We've seen those results very consistently. So this is for 2021. We had the same kind of result when we used 2016 as a common year to evaluate model, and we trained model up to 2015, 14, 13. So we backtested it, and we got the same result. This is just the result that went into the paper that we committed to. Yeah. So you would see the same effect regardless of COVID. Another thing I wanted to mention is the autoregressive loss. There were a few comments about what happens with the autoregressive loss. So this is one of the plots we have in the paper where you can see the same kind of headlight variables, lead time and RMSE, lower is better, and the different shade of blues are different version of GraphCast trained with different number of autoregressive steps. So the lighter blue is just a model trained at one-step prediction, and the darker blue is the GraphCast trained with 12 autoregressive steps. So what you can see is that as the number of autoregressive steps used during training increases, the performance at longer lead time improves. Right? You can look at the relative plot at the bottom, and you can really see that when it's normalized by the 12 autoregressive step version of the model, this is the best model at long lead time. Other models are worse at longer lead time, but they tend to be a little bit better at shorter lead time. So there's a trade-off here that when you train autoregressively, which is something quite interesting to see. One more thing I wanted to mention, one of the limitations of training a deterministic model on RMSE loss is that at long lead time you tend to blur your prediction in order to kind of minimize the double penalty. And so it's not, if you look at the y-axis, it's several orders of magnitude of differences, like when you look at the true spectrum that you should get with respect to the one you get. And you tend to have a little bit of blurring, so you have less power at those very short wavelengths. And in particular for Q700, which is a specific humidity at 700, this is actually the variable that blurs the most in what we've evaluated. And you can really see that there's some massive blurring happening here. So that's one of the limitations that you get from training a deterministic model autoregressively. And just to kind of show you what it looks like, that worst variable that I mentioned, this is a video of Q700 over time. You can see it really quickly blurs the prediction, but there's still some areas where you see some high frequency pattern. So you can still see like pulsing here that is probably due to the diurnal cycle. You can still see like some fine details around the Andes and the mountains. So it blurs kind of selectively like where there's a lot of uncertainty. So those models, did great on scorecards, but people came to us and say like, okay, great, you got good RMSE. What does it mean for doing prediction? Is it useful for anything? So what we did is we looked at what we call downstream applications, so just application of the weather without fine-tuning the model. So the model is not specialized to any of these tasks. We just use the forecast and evaluate them in downstream application. For us, it's just it's another way of looking at the performance of the model. In particular, we looked at predicting the tropical cyclone tracks, so the position of the cyclones, and we evaluated over 4 years of data. The ground truth here is a separate data set called IB tracks, which is a consortium of like different, a combination of several model prediction to like it's a real separate ground truth. And then the HRS forecast is the actual cyclone tracking forecast from ECMWF. So, and in our case, we just run a tracker on top of our forecast. What we could see is that there was, on average, over 4 years of evaluation, 9 hours of improvement for our model. And when you look at paired error analysis, this is like what the improvement looks like, and the error bars are also like that. And just for your understanding, like this is like about a 20-kilometer improvement that would be around here. So really, like, you can really improve the tracking of cyclone with that kind of method. One thing I have to mention is that the prediction of the intensity tends to be not as good. It tends to under-predict the intensity of the cyclone for multiple reasons. That were one of them was mentioned earlier, which is that the ERA5 data is pretty coarse. So the peak of the velocity, which is informing the intensity of the cyclone, is kind of washed out in the data. But there's also the fact that the model is deterministic, which kind of tends to blur as well. So the model, we published the paper, and people were also like, oh, okay, this is great, but we don't believe you. So we open source the model, and this forecast on the right is the first time that it's a forecast made by ECMWF with our model. We kind of helped them hook up our model to their data feed, and I think this is the first cyclone that happened after the model was open source, and they hooked it up to their model and made a nice interface on their website. And what you can see is that was for Cyclone Lee. You can see that the true trajectory is in black, the trajectory forecasted by GraphCast is in blue, and that in red is the HRS forecast. So GraphCast predicted correctly that the landfall would happen in Nova Scotia roughly 9 days before it happened, while the traditional model only caught up to the landfall happening here 6 days ahead. So that's kind of, it works in average in our plot, but also on specific example. How am I doing in time? Well, in the meantime, GraphCast outperforms really the best deterministic operational model called HRES on 90%. 20 minutes, okay, good. On roughly 90% of the 1,400 targets we evaluated, we showed that it's useful for applications such as cyclone tracking, some other things that I haven't shown about like characterizing the strengths of atmospheric rivers, and some result on extreme temperatures. It's really fast for inference. We were talking about 47 seconds on a single TPU, specifically a TPU v4, but there's still some limitation because it's a deterministic model, right? So the next thing we did is to work on the next generation of the model that we call GenCast, which is a probabilistic model. And this is work led by Ilan, shown here at the top left, and recently published in Nature. And the idea, again, is to kind of provide the maximum value for user by providing, instead of a deterministic forecast, an ensemble that can capture the uncertainty of the forecast. And so a lot of the weather we care about, for instance, hail, doesn't happen very often, but is really in the tail of the distribution. But we want to be able to predict that those severe events can happen with certain probability rather than kind of washing the prediction into an average prediction. And so, it doesn't surprise you that the kind of gold standard to do that is to generate an ensemble of forecasts, typically by perturbing the initial condition of a deterministic model. So, by contrast to the prediction that was very smooth from GraphCast, I'm showing the same field but predicted by GenCast. This is now 12-hour steps instead of 6 hours, but it doesn't really matter. This is, for instance, ensemble count 1. A second ensemble member, you can see there's a little bit of difference that evolves over time, and a third member that I overlay with the two previous ones. But each prediction, as you can see, is fairly sharp and doesn't blur compared to the previous GraphCast model. So in terms of difference, GraphCast predicts 83 weather variable. Spatial resolution is still quarter degree, which is pretty challenging for that kind of model. A lot of effort goes into scaling this model to high resolution because that's useful for users. Again, that's more than 1 million pixels per frame. 12-hour steps, we make a prediction up to 15 days, and now an inference costs 8 minutes. And it's going to be a little bit obvious why in the next slide. And we can generate like 15 ensemble member, which is kind of typical in a global weather model. The way the model works is still fairly similar to before. You have some input frame describing the state of the weather at time t. You're trying to predict the next time xt plus 1. The way we do that is by using a diffusion model. So you start by sampling noise with sample noise on a sphere here, and then you learn a function, a denoiser, that is conditioned both on that noise and on the previous frame, and learn to just denoise the noise. And you do that iteratively at inference time, and that's just the very typical diffusion model process. Once you've predicted the next step, you unroll the model autoregressively, same story as before. But now every time you sample a new noise, you get a new different prediction. So you can generate an ensemble by just sampling 50 different noises. In terms of difference of how this model works, I think this is quite striking. It's trained on the same data. We managed to reduce the training time by pre-training at 1 degree and then just fine-tuning at quarter degree, which is a big time saver. And one thing that is quite striking to us is that the model was only trained at one step. So we only train it to predict the next step, and we don't use an autoregressive loss that shows the model how its own prediction error compounds over time. That was quite a big surprise to us. We really expected to need that autoregressive loss, but GenCast just works out of the box like that. We train it to do a very good one-step prediction, and that composes over time quite naturally. In terms of the differences, the denoiser architecture is, the overall model is pretty much the same. The denoiser doesn't have this multi-mesh anymore. We've replaced the GNN by a sparse transformer, so that complicated mesh that I didn't really remove from the plot on the left and the right is something simpler, where every point in the mesh actually gets to learn from like a neighborhood around it that is k hops away. So that's the only, and we use a transformer instead of a GNN for that part. We also used conditional layer norm in order to kind of condition on the noise level. But that's pretty much the difference in terms of architecture. In terms of the training protocol, we follow like the elucidated diffusion model paper. Some of the difference is that we sample the noise isotopically on the sphere. And we have like a weighted mean square error for the denoiser. And at the end of the day, when we do inference, we need 20 solver steps, which is 39 function evaluation in order to make the prediction. So we have 39 forward pass into the network, which is why inference is a bit more expensive with this model than with GraphCast. Maybe I'll try to go very quickly about that. So maybe, again, to emphasize the importance of engineering here, transformers are like really expensive when the sequence length increases. I've said this something like 40,000 nodes, that's square, that's like a large number of a very big matrix. So in order to make that scalable, we use kind of a trick here. We only wanted attention to be local. So if you imagine that the blue points are represented in that array here, and the center point red is here, black dots are the one that you don't want to connect to. You can build the agency matrix for this connectivity pattern, and just put a black dot where, you know, like the red dot is connected to all the blue dot in that picture. So that red dot, we say it's connected to these blue dots, itself, and the other blue dot. And you can do that for every row, and if you do that, you construct this agency matrix that has this shape. So that's pretty hard to exploit, because if you want to do attention, and this is the connectivity pattern, it's very, you might have to do all-to-all connection attention. But if you realize that you can reorder in the node in order to have like this nice tri-banded structure, now you can decompose your computation, your attention, into a bunch of blocks. So now you can loop over that, and you can ignore all the terms in the off diagonal, and you can implement with dense operation the sparse operation. And that works really, really well and can be optimized very, very efficiently. Anyway, so that's just one reason to like care about engineering, because I mean, this was pretty instrumental. In terms of score, aggregate score, you have the same type of like scorecard where you see that GenCast outperformed now the ensemble top operational model, which is called ENS, on 97% of the targets. And one question that we often ask is diffusion adding anything over initial condition perturbation? So is the diffusion really doing the ensemble, or is it just because you put initial conditions that are pretty good that you get an ensemble? And our original result on the first archive paper used a perturbation on the input, and one of the reviewers asked about that. So we removed the perturbation, so we start the ensemble prediction from a single initial state, and we let the noise generated by GenCast to add and create this ensemble. And it turns out that that does extremely well in itself. And we compared that performance to a version of basically a GenCast architecture, but trained in a deterministic fashion. When we add also perturbation in the input. So that's what we call GenCast perturb. It's basically a deterministic version with some perturbation in the input. In that scorecard, you can see that GenCast is, it's blue almost everywhere for CRPS, the probabilistic score. So that shows that the model GenCast is better than the deterministic variant plus initial condition perturbation. Here I'm showing just some calibration numbers. You can see that GenCast is very close to 1. That's the blue line. That means it's very well calibrated, which is very important when you generate an ensemble. There was a question about extremes. So here are Breyer scores for different thresholds, so for different values, so 0.01%, 0.1%, and 1% of extreme as defined with respect to climatology. And you can see that in blue, GenCast is better than ENS, and wherever it's gray, it means it's statistically significant, and wherever it's white, it means there's no, we can't really say it's statistically significant. But what you can see here is that the model is good at those extremes, granted that 0.01% is not very extreme. There's only so much we can say about when you do evaluation in 1 year, you're not going to get like a lot of once-in-a-century events, so I think you have to be very, very careful about claims about very large ensemble and capturing the tails of the distribution, which is obviously very challenging, especially for machine learning methods. In terms of this, I just wanted to show an example with cyclones. So here you have like a real, so specific humidity over Japan. So there's like I think it's typhoon RGBs here. That's the ground truth. Here you have 3 samples made by GenCast. When the forecast is made a day earlier, you can see like the cyclone is pretty much present in the 3 samples. And when the forecast is made 15 days ahead, you can see the samples are very different. No cyclone is predicted. This is the ensemble mean, where you see a day ahead, you really see the cyclone, but 15 days ahead is way too early to really predict it skillfully. And then on the right, you can see the perturbed version of the deterministic model, which completely misses the forecast 15 days ahead and get it okay like a day ahead. The thing that we want to show here is that the spectrum of the prediction, so in pink is the deterministic model, you still have the smoothing that we talked about earlier, but each of the sample, which is the blue spectrum here, match pretty well the red line, which is the ground truth. And at 15 days, it's even worse, where you can see a lot of blurring for the ensemble mean, quite a lot of blurring for the deterministic version in pink, and then the samples in blue are matching, again, pretty well the red line. So it's capturing the spectrum of the prediction quite well. I think I'm going to run out of time pretty soon, so I'll go quickly over like some other applications. We looked at like renewable energy, and as kind of an ideal case, we looked at prediction of the wind at 10 meters at all the location of those blue dots. It's quite important to look at those specific locations because, as we discussed earlier, the position of windmill is biased towards places where there's a lot of wind for obvious reasons. So we want to check for that, and then we compute the wind speed, push that through an idealized load factor to get the energy generated, and we kind of compute the energy produced for different like kind of area, aggregation area, which could represent regions served by a power grid, for instance. What we can see here is the relative CRPS, where black line is the baseline ENS, pink line is the perturbed deterministic version, and the blue lines are GenCast. And each of the dashed line or the different style of lines are different pooling areas for that result. And what you can see here is that GenCast is, again, outperforming the traditional based ENS pretty significantly at all lead times. This is an ideal case. Obviously, you care about like typically wind at 100 meters altitude for windmill, and there's like the idealized load factor that I mentioned. But this is just a proof of concept and another way of measuring the quality of the forecast. Again, we can look again at cyclone predictions, and with Ensemble you can do spaghetti plots for cyclone predictions. So you can see the example on the right, again cyclone at GBIS. So you can see how useful that can be for predicting when a cyclone is going to hit the coast. And this is another example that we looked at just before the publication of the paper, which is Milton, which really made it to the news. And one thing you can do with that type of ensemble is look at quantity that are like probability of strike, for instance. So we looked at, we did that study for Milton, and on the x-axis you can see the dates with the landfall of Milton on the right-hand side. And then the color here corresponds to probability, different probability. So in the center you can see the probability that or forecast predicts that a cyclone is going to hit anywhere at any time, Florida. And you can see that it goes from pretty low, maybe 30% before October 1st, to 90% on October 4th, basically. And you can basically, here the dashed line is the ground truth of the trajectory of the cyclone, and you can create those maps by looking at, for each member that you predict, you look at where you predict the cyclone is going to be, you draw a circle of radius 120 kilometers, and kind of overlap that for many, many trajectories. And you get those maps that we're showing here, where at this point it's quite uncertain whether there's going to be a cyclone. On October 2nd, there's a pretty good chance, maybe above 50%, that a cyclone will strike around here. And as you go in time, you see the kind of this track becoming purple more and more, being quite sure that those points are going to be in the path of the cyclone. So again, that's like quite a very concrete example of what you can do with those ensemble members. So just before I wrap it up, some takeaway message. GenCast outperformed the best ensemble operational model on 97% of 1,300 targets. It's quite useful for real-world application, including like renewable energy, extreme temperatures, and cyclone tracking. Still quite fast and in France. 8 minutes is still pretty good compared to traditional models, and it makes sharp and calibrated forecast. One thing I want to also mention is that those models are open source in the sense that we've open sourced the code, so it's publicly available on GitHub. We've also made the weights publicly available under non-commercial license, so you can use them for your research. and you can test them. You can just use them. But we've also made the forecasts themselves publicly available. So if you don't want to run the model yourself, you can just download the forecast that we make publicly available. We've gone through like a rebranding phase. So now GraphCast and GenCast are called WeatherNext Graph and WeatherNext Gen. And then they're available at those places. So to answer Michael's point about cyclones, our predictions are out there. Come back in a few months and look at what we predicted, and we can see how well they were doing. And with that, thank you for your attention. I'll take any questions, and if you're interested, there's the science paper, nature paper, open source weight and code for GraphCast and GenCast, and then the live forecast on the right. And maybe one thing I want to add is that those models are also, I mentioned some caveats in terms of like their initialization. Those models are now fine-tuned to work with operational inputs, so they run on the same input as HRES. So that's how we are able to kind of make those models run live, and compare them apple to apples to existing baseline. And with that, thank you very much.
Thank you very much.
Beautiful lecture.